Somewhere in northern France, a magnificent cathedral has endured for more than 800 years. For 8 full centuries, it has faced freezing winters, heavy rains, and the constant cycle of the seasons. The ground beneath its massive walls has frozen and thawed roughly 800 times, yet the base of the building has remained remarkably stable. There are no major cracks climbing upward from the floor, no corners slowly sinking into the earth, and almost no modern cement anchoring it in place. Now step inside your own home. Walk down to the basement during a cold February evening, and you'll likely feel the chill seeping upward through the concrete slab. Perhaps you've noticed a thin hairline crack on one wall that wasn't there last year, or a door upstairs that now sticks every spring when the ground thaws. Your foundation was professionally dug deep, reinforced with steel rebar, and engineered to meet strict modern building codes. The medieval cathedral's foundation was not. So why does the ancient structure often outperform the modern one? The answer lies in a simple yet brilliant technique that medieval masons mastered, one that modern builders have largely forgotten. These craftsmen understood the true enemy lurking in the soil and defeated it using little more than carefully placed stone in a well-designed trench. It was a method so effective and durable that it supported some of the greatest buildings in history for 1,000 years before quietly fading from standard practice. This is the forgotten story of the foundation we stopped building. Most people blame winter cold when foundations crack. It seems obvious. The ground freezes solid, expands, and eventually the concrete gives way. Modern solutions follow that logic. Dig deeper than the frost line, pour massive reinforced concrete footings, and hope the cold never reaches the structure. But this approach misses the real culprit. Cold by itself does relatively little damage to a stable, dry foundation. The true destroyer is water, working invisibly underground. When soil containing moisture begins to freeze, something remarkable and destructive happens. Liquid water from deeper, warmer layers is drawn upward through tiny capillary channels in the soil, similar to how a wick pulls oil up in an old lamp. As this water reaches the freezing front, it turns to ice and attaches to existing ice formations, creating thin horizontal sheets known as ice lenses. These lenses continue to grow as long as more water keeps arriving. Because ice takes up more volume than liquid water, the ground expands upward in a process called frost heave. The force generated can be enormous, strong enough to crack thick concrete slabs, buckle highways, and lift entire sections of buildings. It happens slowly and relentlessly, a fraction of an inch each winter, repeated year after year. Over decades, even the strongest modern footing can shift, tilt, and fail. Frost heave requires 3 key ingredients. 1. Freezing temperatures. 2. Soil that can hold and transmit water. 3. A steady supply of moisture migrating upward. Medieval builders couldn't control the weather or completely change the soil. Instead, they cleverly attacked the one factor they could influence: the water. Before laying even a single stone for a great cathedral, workers dug a continuous trench that followed the entire perimeter and layout of the future walls. In many grand cathedrals, these trenches were astonishingly deep, sometimes 10 to 20 feet, and wider at the base, flaring outward like a broad foot for better load distribution. They filled the trench not with mortar or concrete, but with broken stone, rubble, and coarse gravel, carefully packed layer by layer. This single layer of stone performed 2 critical functions simultaneously. First, it spread the enormous weight of the heavy masonry walls across a much larger area of soil. A tall stone wall is incredibly heavy, and without proper distribution, it would sink unevenly into softer ground. The wide bed of compacted stone acted like a giant snowshoe, preventing the structure from punching downward. Second, and this was the genius part, the loose stones created thousands of irregular air gaps. Water cannot easily climb through such spaces via capillary action. Instead of being drawn upward beneath the building, moisture drained downward through the voids and flowed away to lower ground. By removing the water, the builders eliminated the possibility of iceland's formation. No water meant no heave. No heave meant the building remained stable for centuries. A modern foundation typically requires two separate systems: reinforced concrete to carry the structural load and an additional drainage network to manage water. Medieval masons elegantly combined both jobs into one layer of stone. Medieval craftsmen had no soil science textbooks or laboratory instruments. They relied on generations of practical observation. A simple test still works today. Dig a pit beside a stream and pour water over a bed of loose stone. You'll see it disappear downward without climbing back up. Craftsmen who spent their lives working with earth and rock quickly learned what nature was willing to accept. Centuries later, around 1902, the famous American architect Frank Lloyd Wright kept encountering the same foundation failures in his buildings, cracking and shifting with the seasons. He began experimenting with what he called a dry footing, a trench filled with broken stone and no traditional concrete base beneath it. He used this method for the next 50 years, including on his own homes in the freezing winters of Wisconsin. In his later writings, Wright proudly noted that the foundations at Taliesin had remained perfectly static, showing no settling, cracking, or heaving over decades. A medieval mason and a groundbreaking 20th century architect had independently arrived at the same solution because the underlying physics is timeless. Remove the water, and you remove the destructive movement. This wasn't a secret reserved for grand cathedrals. The same principle appeared at every level of medieval society. Peasants building modest cob houses, thick walls made of clay and straw, always raised them on a low stone plinth or base. This kept the vulnerable earthen walls away from damp soil that could cause them to slump or erode. Across Britain, Ireland, and the Mediterranean, dry stone walls, built without any mortar, have stood for centuries. The stones are carefully fitted to lock together structurally, while water freely drains through the gaps instead of pooling and freezing. The craft is so culturally important that UNESCO has recognized dry stone walling as part of humanity's intangible cultural heritage. There was never an official ban on stone foundations. In fact, many modern building codes, including in the United States, still technically permit crushed stone footings. However, the system strongly encourages poured concrete through simplified pre-approved tables, faster approval processes, and widespread familiarity. Using a stone trench often requires hiring a structural engineer and convincing inspectors who rarely encounter the method, turning a potentially economical option into a bureaucratic and costly one. Meanwhile, concrete has become the most consumed material on Earth after water. Cement production alone accounts for roughly 8% of global CO2 emissions. A massive, profitable industry benefits from the dominance of concrete. No conspiracy was needed. Simply making the traditional stone method the path of greater resistance was enough for it to fade. In a typical code-compliant house, problems often develop slowly. One side of the house may have slightly wetter soil due to poor grading or a downspout. Each winter, frost heave lifts that corner a tiny amount. Over years, the rigid concrete slab bends, creating cracks. Water enters the cracks, making the next freeze worse. The damage becomes self-reinforcing. Repairs, involving hydraulic lifting, underpinning, or full replacement, can easily cost tens of thousands of dollars for a problem the original design helped create. The medieval stone trench avoided this cycle entirely by preventing water accumulation underneath from the beginning. For existing homes, focus on keeping water away from the foundation. Install a perimeter, French drain, a trench with clean gravel and perforated pipe, sloped to drain away. Regrade the soil to slope away from the house. and extend downspouts several feet from the walls. These steps are relatively inexpensive and can dramatically reduce frost heave risk. For new construction, on suitable sites, stable, well-draining soil in areas with low seismic risk, a properly engineered stone trench below the frost line, combined with a minimal concrete grade beam, remains an excellent, low-maintenance option. A bed of clean stone doesn't rot, rust, crack, or require replacement. It can last centuries with almost no upkeep. Of course, stone footings aren't ideal for every location. Soft clays, expansive soils, or high earthquake zones often require the strength and rigidity of reinforced concrete. The key is choosing the right tool for the specific ground. We have wrapped the planet in concrete, sometimes reflexively. In 2011 to 2013 alone, China poured more concrete than the United States used during the entire 20th century. Yet on many stable sites, a simple bed of clean, compacted stone could provide superior long-term performance at lower environmental cost. The medieval masons weren't primitive. They were excellent practical engineers who worked with nature instead of fighting it. Their cathedrals still stand as quiet proof that sometimes the simplest, most elegant solution is also the most enduring. The knowledge was never truly lost. It's still there beneath those ancient walls that have barely moved in 800 years. Perhaps it's time we remembered it.